we can start. So please, Timoteo.
Yeah, okay. So good afternoon, good morning to everybody. So thanks to be here to this last lecture. So, okay, I already asked if you have some questions, so please do not hesitate if you have some question now or the end of this last lecture. Okay, so last time we spoke about this idea of how the leopard gets its spot. That is how in the framework of diffusive coupling in a network, how do you have this patchy solution which is called a Turing pattern. Today we will use a different kind of coupling. So I will skip to the first slide of today, which is this one. And so, as I told you last time, there are at least two main directions in which that you can use to couple dynamical system. Last time we used the diffusion light. Today we will study what is called adjacency cap. It means that say the reacting part are stuck on the node and they exchange, I don't know, information, photons, energy, whatever you want, but they do not move. So the object that is moving is the responsible for the interaction, but the people or the object remains in the node. This is an example. I give here two examples. One is this model has been used to study the onset of stripes and spots on this fish, which is called zebrafish. Here is a paper that is in the Dropbox that I shared with Stefanella, where the authors studied this kind of phenomena by studying how nearby cells do interact. In this fish on the skin, he has two kinds of cells, the yellow and the black one. It means the pigmented one and the one without pigments. And because of the interaction among the cells, on the skin of the fish, you can have this kind of color. And in the paper, they show that you can have all this kind of solution once you move a parameter, passing from a spot, say black spot on yellow, then you have stripes, and then you go to a yellow spot on the black background, and so on. And then you can move up and down, having larger spot, a smaller spot, and what is called labyrinth-like, because it's not really striped, it's a bit a mixture. And then we have a recent paper with some collaborators. We studied this kind of generalized pattern in a generic reaction system, but without diffusion, only with the interaction to the neighborhood. Okay, so we use once again this idea of metapopulation that I already told you last time, but that is in each point, in each node, you have enough agents to consider them are well mixed. That is, you can use a differential equation inside each node, but now you don't have this flowing of people or agent across the links, as in the here, but you only have interaction among nearby nodes. Okay, so you react on the nodes that you interact via nearby nodes. Okay. And okay, so also differently for what I did last time. So last time I assumed that the isolate system converge to the equilibrium point, stationary one, which is the same for all, which is a stationary, so it is a number. While here I consider that the isolate system will converge, but to the same solution, which is in this case periodic. Okay, so if you remove the network, all the nodes, so all the system converge to the same function S of t. There was a question last time when I studied the Bruxellator about, yeah, but you're considering the convergence to a fixed point. Yes, we can also consider convergence to this periodic point, also in the case of the Bruxellator. So I prefer to divide the two topics, but of course you can use diffusive-like and convergence to some time periodic function, or you can use the adjacency-like also in the case of a fixed point. So now today I will present you the case of time-dependent solution, and then using this adjacency. So adjacency means that the rate of evolution of the quantities in node I is proportional to some average, or remember Ki is the number of neighborhood of node I, times all the agent, so all the nodes J that are connected to I, times some function F that takes into account the concentration in node I and node J. Okay, so this formula means you take one node I, you consider, so this is I, you consider all the neighboring node J, so the node J is such that Aij is equal to 1 because they are connected, and then you, in some sense, average the quantity that this node receives by dividing by the total number of connection. And then there is some nonlinear function that mix up the things. Okay. Okay, if you use this and you do some algebra. So first of all, I'm sorry, my slide is a bit out. So as the last time, I add and remove the same stuff. This nonlinear function evaluated on the same node xi. So here I have Aij f xi xj. Now I add and remove f in xi xi. So I do nothing. But once you do this, you can take the part with the minus and put together with a. In such a way, you have this delta. So now I have the sum over all neighborhood of Aij divided by the degree as before, minus the identity times this function f evaluated in point I and j, plus this term, which is in some sense the isolated system, because this term here is responsible for the equation x dot I is equal f xi xi. So if I remove the netto, so if I remove this part here, what remains is just this part here, which is an isolated system where each node I react only because of I. Okay, and now we can define this matrix as some, say, L again. And so my equation is again that the rate of increase of decrease of x at node I is again a matrix Lij times some linear function plus this term, which is the isolated system. So now have a look at this matrix Lij. So this matrix is so Aij divided degree minus delta. So it remembers you a little the random walk Laplace matrix that I write here. So for the random walk, the Laplace matrix Lij is equal to Aij divided Kj minus delta Ij. So it's almost the same, except that for the random walk, you divide by Kj, because in this case, if you want to know how often the walk goes on the node I, you have to take into account that it leaves some node J, and so you have to divide by the number of possible way a walker leaves the node J. So that's why here we divide by Kj. In our case, I'm focusing on node I, and so I'm looking how many neighborhood it has. And so that's why I divide by Ki. Okay, so this matrix is again a Laplace matrix that is called in the literature a consensus. Consensus because you are trying to make an average of people, say, discussing around you. So the node I feel a consensus about the opinion discussed in the average node. Or reactive because it's the kind of reaction because of the nearby nodes. So if you write this matrix in a matrix notation, you have this d minus 1 because you divide from the you multiply by the left if you want, where d is the matrix, the diagonal matrix with the degrees. A is again the adjacency matrix, and I is that entity. So this matrix is not symmetric. You can see from here, because even if the network is symmetric, so Aij is equal to Ji, but because you divide by Ki, but this is different from Lji, of course. Okay, so let me just write explicitly. Lij is in general different from Lji. So because the matrix is not symmetric, you cannot use the theorem that tells you that all symmetric matrices can be diagonalized and they have a real spectrum. However, you can prove something, which is the following. You can introduce this new matrix, L-sim for symmetric, which is indeed the Laplace matrix that we saw last time. So A minus D is the Laplace matrix that we used last time for the diffusion-like method. And you multiply to the left and to the right. Okay, so this matrix L sim is nothing but, so L symmetric Ij is the degree to the square root, and this is, you can do this because the degrees are positive, so the square root is well defined. So is 1 over the square root of degrees on node I times Aij times square root of degree on node J minus, you have d minus 1/2 times d times d minus 1/2. So this is the identity. And so now this matrix L sim is by definition symmetric, because you can see you have Ki to the left and to the right. And so if you exchange here I and J, you also exchange I and J there. And so this is a symmetric matrix. Being symmetric, these matrices are, so is again a sort of Laplacian, so it can be diagonalized. The spectrum is non-positive, means you have 0 again as eigenvalues, and then all the other are negative. Okay, and then how you can relate this matrix to the one that I'm interested in is just one more step. The matrix L, the consensus that I'm interested in, is indeed similar to this L symmetric. It's just simple computation. If you take L symmetric, this is defined over here. So let me write again L sim. So maybe let me write it on your page. L symmetric Ij is equal 1 over square root of Ki Aij 1 over square root of Kj minus delta Ij. Then I say I multiply to the left by square root of the degree and to the right by square root of the degree. So if I take this matrix, I multiply, I divide because is minus 1/2. So if I divide by square root of Ki L symmetric Ij, and then I multiply to the left, the right, sorry, by square root of Kj. So I obtain 2 times, so square root times square root gives you 1 over square root of Ki, and sorry, not square root, 1 over Ki. Then you have Aij, and then when you multiply to the right by square root of Kj, but here you have the division by square root of J, so this gives you 1. And then at the end, here, because you have the delta, at the end here, you end up with, again, delta Ji. And so this is by definition the Laplacian Lij. And so I prove that the two Laplacians are related by this matrix D minus 1. And so because they are similar, they have the same spectrum. So this means that also this matrix that is not symmetric, it has a real spectrum, which is negative in this case, except for 0. You can prove that indeed the spectrum is bounded between -2 and 0. It's a small proof that can be done. And another point that we'll use in the following, this matrix again sum to 0. So if you sum on the row or the column, you sum to 0. This means that again, as I told you, you have 1, 0 eigenvalues, and then this is the eigenvectors with all the ones normalized by the square root of n. Okay, so we have a few properties of this function L, which is the consensus Laplace matrix. And what is important for us is the negativity of the spectrum, the fact it's real, of course, and that this sums to 0. Okay, once you have this one can do the application that I'm interested in. And I decided to present this kind of application in the case of the Stewart-Landau. So if you remember, the Stewart-Landau was the model that I used to show you the bifurcation of the limit cycle by the Hopf bifurcation. So in the, I think, first lecture, or maybe the beginning of the second, I show you how a fixed point stable can bifurcate into a stable limit cycle. And the model I used was the Stewart-Landau. So maybe it was not exactly the same equation with the parameter, but after all, it's the same model. Okay, so the Stewart-Landau is the following. You have a complex variable because, as I told you, this is a complex oscillator. So you have Z, you have a phase, a complex phase, an amplitude. And so the question is the derivative of Z with respect to time is a linear part, which is sigma times Z. A sigma is a complex number. So it has a real part and the imaginary part, I use the notation to denote the real part with this small r to the right of sigma of the variable, and the imaginary part with this I is indeed a small I, is the imaginary part of the variables, okay? And then in the equation, you have minus beta times the modulus of z to the square times again z. So this is a third order term, so it's non-linear model. And again, you have this parameter beta, which is again a complex number, okay? One can show easily that this function admits a periodic solution. The periodic solution is this one with this frequency omega. So we can do the computation. It's not so difficult. So let me just copy, change also the color. So so you have z dot is equal sigma z minus beta z square times zeta z, and then so the better way to do this is just let me, oh sorry, so just verify if you want. It's easier, it's faster. So I have the real part of sigma divided the real part of beta times AI omega t. So you put this formula into the equation. So once you derive with respect to t, the only thing that depends on time is this exponential. And so once you derive z dot, it's just 1 I omega z, because everything else is constant. So if you put this information in your equation, you have I omega z is equal sigma z minus beta modulus, well, let me write it, z to the square times z. So first of all, you recognize that z is not 0, so you can divide by z in this equation. And so you remove z. Second, here you have the modulus of z. So this is equal to sigma minus beta. And the modulus of z, being this part with modulus 1, is just the modulus of this quantity, but is squared. So is sigma re divided beta real part. Okay? Then let me use explicitly the expression for sigma and beta. So you have that sigma is sigma real part plus I sigma imaginary part minus beta real part plus I beta imaginary part multiplied by sigma real part beta real part. So let's just copy this part. And I go there, hop, want to, oh, okay, don't worry. Okay, and so now if you develop this term, you have real part of sigma plus I imaginary part of sigma. Then you have beta real times, so this terms times this one gives you only the denominator. So this is a minus sigma real. And then you have minus I beta imaginary sigma real divided beta real. Then you see that the sigma real and sigma real cancels. There is one I that is on the left and the right. So at the end, you have omega is equal to sigma imaginary minus beta imaginary times sigma real divided beta real. And indeed, it is what I wrote in the first equation. Omega is imaginary part of sigma minus imaginary part of beta times this ratio, which is exactly this equation. So I show you that indeed this formula, this equation, so this function of time is indeed a solution, because once you plug it in the equation, it gives you left-hand side equal to right-hand side. So this means it's a solution. And this also provides you the frequency of the motion. Omega is exactly equal to this quantity. Okay? Okay, so you know that there is an equilibrium, and this is the function S that I showed you in the beginning. So this is my S of t. This means that if all the system, so if you have n copies of the same Stewart-Landau model, you can prove that this limit cycle, I think we will prove in the few next slides, so that this limit cycle is stable, and so all the solution converge to this limit cycle. the question is then, okay, let me now couple together different Stewart-Landau equations. What happened to the stability of this limit cycle? Will it remain stable, or it can be destabilized because of the connection? Okay, so let's now study the stability of this limit cycle. So to study the stability, what does it mean? What it means? Take a solution which is closed in some sense, and look if this closed solution converge to the initial solution. In the case of the fixed point, it is easy. We already saw this last time. You take the equation, you compute the Jacobian, you evaluate the Jacobian on a fixed point. This gives you a matrix, you compute the spectrum of the matrix. If the spectrum is negative, everything is okay. Here is a bit more complex in principle, because even if you compute the Jacobian and you evaluate on this function, this is the function that depends on time. And so you will have a Jacobian which depends periodically in time. And so this in principle implies the use of the Floquet theory that I told you at the end of the second lecture. But indeed, as I will show you in a while, I also choose to use this Stewart-Landau because it is some magic miracle that once you compute the Jacobian, evaluate on this function, the Jacobian is a constant. So indeed, you can do everything analytically because of this special feature. In general, if you have a time-dependent system and you linearize, the Jacobian will depend on time. So you cannot use this idea. Okay, so how can you linearize your system around this periodic solution? Okay, you take your periodic solution and you add a perturbation. I decide to add the perturbation in the following way. I multiply by 1 plus rho, where rho is a real function, small in some sense, times exponential I theta of t, where theta is another real function, again small. What does it mean small? If rho is 0 and theta is 0, you end up with your initial solution. So if rho is small and theta is small, you can think that you are nearby this time evolving solution, and so you would like to study the stability. Okay, so this is what we are doing right now. So today is a bit computational, but I think it's good. So let me write my system. So this is my initial system. And this my, so let me try to see the solution. Z hat is equal to square root of real part of sigma divided real part of beta times A E I omega t. And then so I write, as I told you, in this way, times 1 plus rho times E I. Okay, so now what you have to do, you have to take this potential solution and plug it in the equation of motion and see under which condition the parameter you can prove that rho and theta goes to 0. This means that this solution will be stable. On the other hand, if rho and theta will go away from 0, say they increase exponentially, then you are proving that this solution Z hat is unstable. Okay, so let us do the computation. I took also some notes because it's very easy to make some mistake in this script. Okay, so let me take, I have first to take the derivative. So the derivative of this function is the derivative of Z hat times 1 plus rho times E I theta. So it's the product, so it's the sum of the derivative of each term. So Z hat, the derivative of 1 plus rho is just rho dot E I theta plus Z hat 1 plus rho. The derivative of exponential I theta is I E I theta theta dot. Okay, and just remember what we do previously. The derivative of Z hat is just I omega. So I replace the first term by I omega Z hat 1 plus rho A E theta plus Z hat rho dot E I theta plus Z hat 1 plus rho I A I theta theta dot. Okay, and then you have to put also this potential solution on the right hand side and do all the computation. So let us do it. Okay, I continue on this page. So I have sigma Z hat 1 plus rho E I theta minus beta. Now you have to take the modulus. So the modulus of z hat, we already know it is equal to real part of sigma divided real part of beta, and that's all, times so rho is okay, let me use the modulus. So 1 plus rho to the square, and the modulus of exponential is 1 because theta is a real function, so I don't have any terms here. So this is the part beta modulus of z to the square times z, so times z hat 1 plus rho times ei theta. Okay, and now you have so let me put here equal. So you have these two equations. Okay, you can already recognize that all the z hat cancels to the left, to the right. So you have let me change color if you want. So you have on the left, on the right, all these z hat that go away. The same is true for the exponential, because you have exponential here, exponential here, exponential here, exponential here, and exponential over there. So let me rewrite or copy what is left. So you have on the first term you have I omega. Let me write. So I have now to do one I omega 1 plus rho. So the first term. Then I have rho dot, which is the only term that remains in the second part. And then I have 1 plus rho I theta dot. So 1 plus rho I theta dot. And this is equal to the first term here is sigma times 1 plus rho. Sigma 1 plus rho. Here in the second term is minus beta times this term. So let me write here. Minus beta times real part of sigma, real part of beta. Then I have 1 plus rho to the cube. So let me observe that because rho is small, I can assume that 1 plus rho is close to 1, so it's positive. And so I put these terms, which is a modulus, with this one, which is without modulus. So I can write this like 1 plus rho to the cube. Okay. Okay, so now let me just do one more step. So I have 1 omega, the first term there, plus 1 I omega rho plus rho dot plus I 1 plus rho theta dot is equal to sigma plus sigma rho minus beta sigma re beta re, and then I have n1 plus this one. Now remember that I assume that rho is small and theta is small. So I also assume, okay, it is small. So this means that in this term here, so in the cubic term, I only take 1 plus 3 times rho, because the remaining part are terms in rho square and so on, and so you can neglect them. Okay, once you do this, you recognize that this term here, that let me circle. So this term here, I omega plus sigma plus the minus beta real part of sigma divided by the real part of beta is 0, because they are exactly the same. It's the definition of omega. Was on the page before. Okay, so all these terms sum up to 0, and so at the end we end up with I omega rho plus rho dot plus here again you have so let me write I theta dot. Okay, let me write everything plus so here you have rho times theta, because rho is small and theta is small. Okay, it's not completely true, but you can assume that also rho times theta is small. So I don't write down these terms. And so I end up with here I have sigma rho minus 3 times beta real part of sigma divided by real part of beta times rho. So I think I put everything inside. And now you have to use again the equation for omega. So let me copy and go to the next slide. So I think it's a bit long, but I think you have to do it at least once. So I think it's a good point to do it right now. So remember, omega was, so I, it was, I don't know, I have to check in my notes because omega was imaginary part of sigma minus I, imaginary part of beta times real part of sigma divided the real part of beta. So this is I omega. This should be multiplied by rho plus rho dot plus I theta dot is equal to rho. So again, rho sigma, let me write it as sigma re plus sigma imaginary times rho. And then you have minus 3 times, again, you have beta real plus I beta imaginary times sigma real beta real times rho. And now you have to collect together terms that are real and terms that are complex. Okay, let me start with the real one. So you have on the right, you only have rho dot. Is it the only real term that you have on the right? While on the left, you have sigma real times rho, but then you also have this minus 3 beta real times sigma divided by beta times rho. So this gives you minus 2 times real part of sigma times rho. Okay. And on the imaginary imaginary part, you have on the right, you have of course theta dot, and then you have this term here, so plus imaginary part of sigma minus beta imaginary part sigma real part divided by beta real part, and on the right you have sigma imaginary part. Sorry, I forgot the rho. On the right, I mean, you have I sigma imaginary times rho, so sigma imaginary times rho. And here you have minus 3 imaginary part of beta sigma real divided by beta real times rho. So if I didn't do any strong mistake, okay, this part simplify because you have an imaginary part of sigma on both left and right. And this part here is the same as there, but you have minus 1 and minus 3. So at the end, I just cancel a small part here. So at the end, the equation for theta dot is equal to minus 2 beta imaginary sigma real beta real times rho. So let me check if I didn't do a mistake. Okay, I don't know if someone follow me, but it seems to be correct. So at the end, okay, if everything is okay, so I go back to my slide. So at the end, I found this equation for the evolution of rho and theta. So I have that rho dot is equal minus 2 times the real part of sigma times rho, and theta dot is the minus 2 times the imaginary part of beta times the square root times, sorry, sigma real divided by beta real times rho. Okay, and so if you compute the spectrum of this matrix, you end up with the, so the eigenvalues here are lambda equal to 0 because you have this 0 here. And this is always true because once you have a periodic system and you linearize, you always have a 0 eigenvalue. So it is the one that is along the flow. So along the flow, you neither contract, neither expand. You just go along the flow. So we always have these 0 eigenvalues. And the other one is minus 2 times sigma real part. And so to have stability, you need that the second eigenvalues should be negative. But if it should be negative, it means that sigma real should be positive. Okay, and because sigma real should be positive, if you look at the solution that we start with, is that you have on the square root the ratio of sigma real divided by beta real, and you want this function do not have any extra complex terms. So you need that this ratio is positive. So this means that you also have to add the real part of beta is positive. So the stability of this solution fixed, so not fixed, but give a constraint on two parameters. Sigma should be a real part and beta should have a real part. Okay, so under these two conditions, we have just proved that the Stewart-Landau equation admit a periodic stable solution. So if you start nearby in the complex plane, you will converge to this periodic solution. Okay, so the next step is now, okay, couple together several Stewart-Landau equations and see what happens. Okay, so if you do this, now you have to add a new index, which is the index of the node. So you have on each node the same equation. So this means the same parameter, beta and sigma, with the same constraint that the real part of sigma, real part of beta is positive. But then you decide to couple together. Okay, you have several ways to couple together the nonlinear system. I decided here to take one, maybe the simplest one, but just to explain how does it work. So I decide to couple together the linear parts. So my equation has a linear part and a nonlinear part. Okay, so here I decide that at a node J, the variable Zj fields the impact of all nearby ZL. And then I divide by the average again, by Kj to have the average, okay? So I have to deal now with this equation, which is for the nonlinear part, the same as before, but for the linear part, a linear combination of the linear part I had before, okay? And then if you add the Laplace matrix that I showed before, you can realize that indeed adding this one with respect to this matrix here. So I remember that AJL divided KJ, so LJL is the adjacency matrix divided by the degrees minus delta JL. So because I add this matrix, I also have to, I remove minus delta, so I have to add somewhere plus delta, and adding this delta gives me this term. And so now if you realize what I have is that the coupled system, so the evolution of Z in the coupled system is the isolated system. So this is exactly the system that I just studied, exactly the same system, to which I add this part, which is decoupling. So if decoupling is 0, so I don't consider the network anymore, I end up, as expected, with n isolated system, Stewart-Landau, each one converging to its own limit circle because it's stable for the condition that I just used. But now you have these new terms. And the question is it possible that new terms change the stability of this solution? So is it possible that it destabilize it? The answer is yes. It is a bit, okay. I didn't prove because it's the same the proof the last time, but you can show easily that this solution, so the solution for the limit cycle, is also a solution for the coupled system. Why? Because if you plug this solution that does not depend on the node anymore on this part, this is at 0 because of the computation that I just did. But if you plug these terms here, this gives you at the end sum over L, the LJL times a function Z hat that does not depend on any index. And so because the sum of L is 0, is also 0. And so we have just proved that Z hat is also a solution for the coupled system. And so the question is it stable or is it unstable? Okay, the computation is a bit more longer than the one I did before, but it's exactly the same. So I think I will not have time to do it. Please do it. If you have any problem, just drop me a mail. We can check the computation together. But it's really exactly the same thing. You take the same perturbation, say, but now depends on the node. So you have rho j and theta j, but they still are small. You plug this equation into the equation of motion, this one. You order the terms according to only the first power, and you collect the real part, the imaginary part, you do all the stuff, and in the end, you end up with this equation, which is this part is exactly the same as before because it is the isolated part. So this is the part that comes from the isolated system. And then you have this new part, which is where you recognize the Laplace matrix. And this new coupling, in some sense, it depends only on sigma. Beta does not enters in the coupling, is of course, because I only coupled through the first part, where this is sigma, I know where is beta, okay? Okay, now you have this equation, and we would like to understand if this system now is stable or not. If that means that if rho j and theta j goes to 0 or not as time goes on. And so we use the same idea that we use for Turing, that is, we introduce again the eigenbasis of the Laplace matrix. So I have now these vectors of phi alpha, and so I project my rho j and theta j on this basis. So I have new coefficient rho alpha and theta alpha that are indeed function of time. If you do this, you plug into this equation. Okay, for the first part, nothing changed. And the second part, but you just realize that once you apply the operator L, so the matrix, to phi alpha, by definition, you extract the eigenvalues. And so this equation over here, it becomes this equation down, where you have now the same linear evolution, but in the space of Fourier, or in the modes. And then you have again this extended Jacobian, they call J alpha, which is J0 plus the eigenvalues times the new Jacobian J2, which is this matrix over there. And the question is it possible to find some lambda alpha, which is negative and larger than -2, such that this matrix has a positive real values? In such a way, it is destabilized. Okay, as I told you at the beginning, what is important here is that this part, indeed, all this part does not depend on time. So even if the solution Z is time dependent, for the Stewart-Landau, the Jacobian part is a constant. So it depends on parameter, but not on time. And this is important because otherwise, what I'm doing now will be no longer true, because if this J depends some time, you should use some Floquet theory. You cannot use what I'm doing now. Okay, so this is important, and this is only because I use the Stewart-Landau model. Okay, so again, because you have this constant matrix, this is a 2x2 matrix anyway. You have to prove, you have to compute the spectrum. You have to solve, so again, the second order equation is the same equation that we use for Turing, even if now is a completely different field. And so the instability can obtain, or if the trace is positive, or if the determinant is negative for some alpha. Okay, but remember, the trace, what is the trace? Is the trace of J0 plus the trace of this part J2, but the trace of this part J2 is lambda times this part over here. And so the trace of G2 is only lambda alpha times two times real part of sigma. But I show you that the real part of sigma is positive, because otherwise you don't have stability. So this is positive, this is negative. So all this part is negative. We already know that the trace of J0 should be negative to have stability of the linear part. So the trace of J alpha is always negative. So you cannot have this first condition. So you can only destabilize your system if the determinant is negative. Okay, I pass the computation. In this case, the determinant is very easy, is a second order polynomial. And so you can prove that if lambda is large enough, so it's larger than this quantity, then you can prove that you have indeed instability. So here you have your coefficient, and so you have your model. Here you have your spectrum, your network. So if the network is such that these eigenvalues exist larger than this one, then you can destabilize your solution. If your network is not able to do this, also the coupled system will converge to the same solution. Okay, so let me just now show you a few examples. So I took this example from the paper that I quoted at the beginning of the lecture. And I have on this picture two networks. So first of all, I fix the real part of beta and sigma 1. They should be positive, so I fix them just to 1. And in this, let me magnify. So in this part here, so this is the plane, imaginary part of sigma, imaginary part of beta, so the only two remaining parameters. And I plot this quantity. So this quantity is the boundary of the condition that I have to impose, because this part is positive, so no problem. the only this part is what it remains. So I'm plotting this part here, and so this is a so all this part here, you cannot have a pattern because this quantity is positive. Remember, the spectrum is negative. So and then in this part with color, this quantity is negative, the minus 50, 100, 200, and so on. And so if you can have eigenvalues lambda that fall in this part, then you are proving that you're instability. And so if you use the same plot that I showed the previous lecture, that I use this relation dispersion, again, you have this kind of curves where you put all your dots that are your spectrum, and you see that here you have a part which is positive. Observe that now these curves all start at 0. It should, because 0 is always an eigenvalues for a time periodic system. And so they should start on 0. But then they could go down or up. In this case, they go up. So just the two networks that I use is a Watt-Strogatz model and a lattice. So here, if you zoom in this part, you have that each node is connected to the first 6 neighborhood on the left, on the right, and then each one is again so connected to the left and right, but you cannot see in this level. And here down, you have this kind of patterns that now looks more like, okay, it's not the spot of the jaguar, but look more complex than just spots of color. So you have this kind of waves that are spread around the network. Here, I only order the nodes from, say, 1 up to 100, but there is no reason that the 101 is with the 101. You can reshuffle them. So, but what is important here is that you indeed have this patchy solution. So you have a time-dependent solution, which is no longer periodic. So this is, you have a phenomenon that emerged spontaneously because of the coupling. If you remove the coupling, everything goes to 0. Because of the coupling, you have this kind of patterns. Okay. So just a few words. So I assume now that the system was periodic and the Jacobian does not contain any longer time. This is not always the case. In particular, this is not the case when your system is chaotic. And there is a large number of papers by these two authors, Carroll and Pecora, that study the synchronization of chaotic systems. So you can think of just two systems, one, I don't know, a Lorentz system, and one Rossless system, so two chaotic systems. You couple them with some network, and then you can discover that they synchronize. So two chaotic systems can synchronize. So it's called that one become the master and the other become the slaves. So the slaves follow the master. In some sense, the Rossless system is obliged to follow the Lorentz one, or vice versa. It depends from the coupling. Okay, or you can take several copies of the same, say, complex system. I don't know, again, the Lorentz system, and you couple them, and you can ask if everything is chaotic or not. So to study this kind of behavior, you have to resort this master stability function, which is nothing but the use of this linear system where now the matrix J depends on time. And so studying this linear system where the matrix depend on time, you are in the framework of master stability. And so if you can show that this master stability as positive Lyapunov exponent, then your system are desynchronized. While if the Lyapunov exponent is negative, then the system are synchronized. So I put here a few papers by these two authors, Pecora and Carroll, and all the papers are on the Dropbox. So Stefanella, you can share with your student. They are quite old paper, but they are still active. I think there are also papers on for the last year or 2 years ago where they study synchronization of chaotic system by changing the topology and so on. So this is an active research field. It's a bit more complex than just Turing pattern or Stewart-Landau, but is very active. It's more numerical one because once you have this time-dependent system, you cannot do almost anything analytical, but in some cases you can. Okay, so I'm quite out of time, but as I propose to you also a few minutes beyond the network. So up to now, we studied everything on undirected network, so symmetric network. But you can go beyond this in several directions. First of all, you can take into account directionality. I already spoke about this. Node I can send or can fill node J, but the vice versa is not true. In case of friendship, this is for sure. In case of other models, you can have that A influence B, but B doesn't influence A, and so on. So it's really important to study this directed network. Another possibility is to use this kind of multi-layer networks. Instead of have just one layer, think of transportation. You have the ground level where there is cars, cycles, and so on. But then you have the underground level with the underground and so on. But also you can have the up level with flight. And so if you want to study, for instance, how a virus spread, but you can be interested in study how the virus spread on the ground level, buses, trains, and so on. On the down level, we use the underground, or in the up level using flight. And of course, if you use flight, you go very far away with respect to foot or underground. So it can be interesting to study also what happens in terms of pattern asynchronization on a multi-layer or multiplex network. There are two names for almost the same stuff. It's a bit small differences, but are not relevant for us now. Or we already spoke about this. You can have temporal networks, so networks where links are created and destroyed because of evolution of time or because they react to the state of the system. This is also a quite recent research field where people now are trying to prove again all the stuff, all the machinery that is true for fixed network to the kind of temporal network. Or you can go beyond the pairwise interaction, because as I told you, in all this example that I show you, I said node I is connected to node J, and they interact in a direct way or not direct way, temporary or not temporary. But in reality, if you think that how people do interact, they do not interact pairwise. There is a group of 3 persons or 4 persons, 10 persons discussing together. And if you have 10 persons discussing, it's not as if you discuss pairwise with the 10 persons. And so this idea of high order structure has been recently expanded and studied in different ways. One way is this simplicial model. So simplicial complex is, in some sense, you have a triangle is a 2 simplex, a pyramid is a 3 simplex, and so on. So you have this regular structure where you have all these regular high order polyhedra. And so here I quote here 3 recent papers. One is the 2019. I think this one is sure. I don't see the. Okay, is the 2020, and the latter one is 2021. So in the 3 last year, you have quite a lot of paper where people are interested and study exactly this beyond pairwise interaction. So study which is the impact of the fact that you discuss in 3, 4, or whatever, instead of discussing pairwise. And one can show that there is a strong difference between interacting in groups instead of interacting pairwise. Okay, so now I prepared several examples. Just say me stops
can
one
I
time.
Can I ask something? This simplicial, so this study the topology of the network, no?
Sorry?
This has to do with the topology of the network. If we reconstruct from the data, this higher order interaction network, this is.
Yeah, so it is called high order interaction network, but indeed they are not network in the sense of pairwise interaction.
Yes.
They call high order network. It means that here you have some new idea that I show you in few slides, where you model the fact that 3 nodes interact at the same times.
Yes, so
but they do not interact pairwise, they interact together.
Yeah, but topologically you represent by a triangle where they are all connected.
Yes or not, because if you represent as a triangle, you are thinking that the edges also exist.
Yeah,
but maybe it's not the case. Because say, imagine we write a paper in 3 persons, a scientific paper. It's not the same thing that writing 3 papers pairwise or 1 paper by 3 persons. So if we write a paper in 3 persons, we are at the same table. Okay, there are of course the pairwise interaction, but it's the group interaction which is more important. So indeed, this is the point that if you want the small negative point of simplicial model, where in a simplex, if you have a triangle, you also have all the edges.
Here not.
While there are more general models where if you have a triangle, stop, you have a triangle. You are not obliged to have the edges.
Mm-hmm. And so,
yeah.
So in a way here you can say in this new model, you can say that maybe you don't produce a paper if there are not all the three authors, no?
Yeah,
And so I'm trying to translate this in epidemiology way. So you might say if they are not, or a recipe, if you don't have all the three ingredients, you might not have an epidemic.
Yeah. So in terms of epidemics is difficult, but if you think in terms of fashion or opinion, so if we meet pairwise, maybe I'm not able to convince you to buy something. But if you are three persons that we all bought something, and we speak to you and say, Stefanella, buy this, buy this, buy this, at the end you are convinced. So in this case, it's really the fact that we are 4 against you. So in our group of 5 persons, the fact that we are 5 together implies that we infect you by exchanging your ideas or your opinion.
So this is used. This is used for election, for example.
Yeah, for election, for fashion, for selling things. Okay, for the values is a bit different because of, of course, if we are together, the chance to have the values is higher, but there are still the binary interaction in this case because I can send my values.
Yeah, but for example, we have in dengue, we have that the mosquito can carry more than one virus at the same time. So
yeah,
maybe the fact that you can be infected at the same time by different things, it allows, and this I think is a little bit true, but I have to look for some reference. They were mentioning this about COVID, you know, at the beginning, at least last year, that some people had it, but didn't explode, so to speak. And then they infected, and then there was a case here where someone had a urinary infection. And then suddenly she became symptomatic and died quickly. So maybe this could be.
Yeah, maybe this kind of, I heard there can be, I don't know. You have to check, see what is the model that they produce your data.
Okay, sorry.
So as I say, now I have several slides. So of course I have no time to show you all of them, but the slides are available. So if you're interested in some slides that I have no time to spend on, just again, drop me a mail, I will answer, or you can have a chat and discuss. Okay, so let me now show you briefly some results about Beyond network. So the first one is this directed network, because it's the more easy in some sense. So and I show you using this diffusive coupling. So the point is always the same. You have node I, you look for the evolution of quantities in node I, and you couple with this diffusive. So again, as the fixed law. The point is that now, once you sum Aij on this part that does not depend on J, you have the degree, but only the degree of incoming connection. So in the second slide, in the second lecture, or in the third one, remember, these terms were just the degrees. Now you have to make a difference between the outgoing degree and the ingoing degree. So here, there is the ingoing degree that matters. And so you end up with a Laplace matrix, which is still a combinatorial direct Laplace matrix. The point, I'm sorry, here I didn't put this in, all the in degree. The point is that now you don't have any more a symmetric matrix. You cannot do as before this stuff or multiplying to the left, to the right. And so you cannot prove that this matrix can be diagonalized and so on. But assume is it. The point is that the eigenvalues now are complex numbers. And this will play an important role, because if you repeat all the stuff, the machine that I did to you before, you end up to study the stability of the system using this equation. And this is easy because here the network doesn't enter. And so you have the trace negative and the determinant positive. But once you study so you project on the eigenvector, assuming to exist, and you study the instability or stability of the coupled system, and you have this equation. Now the point is that now inside these matrices, you have complex numbers. And so the equation that show you, so I can write explicitly lambda equal plus or minus trace and square root of determinant and so on. But then now inside there are complex variables. And so if you do the analysis, and that's been done in this paper of 2014, you end up with some new properties. And the best way is to show you in this here on the left, where now you have a plane where the real part of the eigenvalues and the imaginary part of the eigenvalues. These two parts here are computed analytically and gives you the condition for which you can have instability. And now you can prove that if you take your network, it now has a complex a spectrum. If the spectrum fall inside any of these two regions, then you are destabilizing your system. While if your network still complex, still direct, fall in the white region, you cannot destabilize it. And indeed, here on the right, you have the usual picture or the dispersion relation where the colors are the same. So you can see that this continuous line is the line for the symmetric network. So you take a network and you symmetrize it is negative. So you cannot have patterns. Everything goes to equilibrium. While if you take the blue one, because it has some part of the spectrum in this zone, the points are detached from this line. Indeed, they can reach positive value. So as I told you this time, the point positive means that you have instability. Also, the red one is the same. You have few red ones here in this part. And so they also detach and are positive. Why the green one, sorry, in this case, I didn't choose the good picture because here the green one are also positive. But you can have some cases because there are a few points here. But there are some cases where the points, even if are directed, are detached by the continuous line, but are still negative. So in this case, you cannot have patterns. Okay. So I already told you about the multiplex multilayers. Again, you can do everything the same. The point is that now your system is more complex because you have, okay, the reaction part, the diffusion part as before, but now you have diffusion across layers. So assume you have only 2 layers. You can diffuse on one layer to other layer, or you can diffuse across layers. And this diffusion across layer, in the case of only 2, is an extra term that is added in your equation. This means that once you compute the Jacobian matrix, so you linearize and so on again, you end up with a matrix which is more complex because now you have a new Laplace, which is called a Superlaplace Matrix, that now takes into account the diffusion on one layer, on the other layer, and across the layer. And then you can be interested to study what happens if you play on these 2 parameters. So if these 2 parameters are 0, the layers are there, but they are not connected. While if you switch this parameter positive, then you connect the layer, and then you can prove that you can have patterns. And this is what has been shown in this paper that I wrote with some collaborator some years ago. Here's just a representative picture, all the same. You have this kind of line that if they're positive, this means that you are creating a pattern. Another example is time-varying network. So as I told you, the main used example is what's called contact network. So the fact that I phone to someone, then I stop someone else's phone. So networks where it's true that the links are created, destroyed, but they last for some minutes, if you call 1 minute or from an hour, and then they disappear, and then they're created after in time. So this means that indeed your network doesn't vary slowly or continuously in time, but it's like if you have some snapshot of your networks and you have, so at each snapshot, few nodes that are connected together. So this is a simple example of time varying network. In this case, there are, I quoted 2 papers, one of my group again, another by another group in Ireland, in Japan, or now is in the US, where we studied the emergence of Turing pattern on time varying network, but also the effect of this time varying network on the epidemics. So, and in these 2 papers, it has been proved that the time variability in the network can induce this heterogeneity. So again, here is a phenomenon where high order, if you want to, time varying is important for the emergence of the instability. And okay, this is just, so I skip this part just to quote, if you use again one result from dynamical system theory, which is the theorem of average. So if you have this kind of, you have 2 networks in the example here, you have 2 networks. So the networks where 1, 2 is connected, 3, 4 connected, and 6, 5 is connected. and another network where 2 and 3 are connected, 5, 4, and 1 and 6. And now you play by switching these two networks. You pass from this network to this one, the first one to the second one, and so on. And one can prove that if you switch the two networks in such a way, you can use some sort of theory of average. So this is a theory that tells you that if you switch fast enough, indeed, you are following the average. Then you can prove that indeed, even if on each snapshot you cannot have instability, on the average result you have instability. So it's again a theorem that we prove where the time varying, fast time varying induces this kind of emergence of new solution. So this is what we spoke before, the simplicial complexes, that is the fact to represent things as edges, triangles, tetrahedron, and so on. But as I told you, a more general way, that it is a hypergraph. Now, hypergraph is really one hyperedge is just a set of nodes. Okay, so it's a really general definition. So you have your nodes, then you put them together in coupled by 2 or in group of 3 or whatever you want. So you have hyperedges that are set of nodes, and then you can have in the same hypergraph a very different number of hyperedges with different size. And if you do this, you can encode this structure with a matrix. Again, it's called incidence matrix, which tells you if node I belongs to hyperedge alpha. So if yes, you put 1. It's something like the adjacency matrix, but in case of I incidence. And then you can construct the hyper adjacency matrix taking E transpose, or the hyperedge matrix taking E transpose E. So I have no time now to explain all the details, but if you're interested, I can send you. But using this new way of encode high order structure, you can prove interesting stuff. For instance, we show that if you take into account the size of the hyperedge times some power, and then the fact that the nodes I and J belong to the same hyperedge alpha, then you can write this matrix Kij, which in some sense fills the fact that node I and J are in the same hyperedge, but they also, the size of the hyperedge does matter. So if tau is positive, the larger hyperedge are more important. If tau is negative, the larger hyperedge are less important. Using this matrix, now you can do everything you did with the networks. If you can study, for instance, random walk or Turing pattern or synchronization on this kind of hypergraph. So here we study the random walk on hypergraph, but I think I also have somewhere, maybe I don't remember if I put, yeah, okay. But you can also study a generical dynamical system on hypergraph, and you can prove that the patterns that you obtain are more sensible to the size of the hyperedge. In some sense, a network is an hypergraph where all the hyperedge have size 2, while in hypergraph you can have hyperedge of size whatever you want, so large as you want. Okay, and okay, there are some applications to community detection that I skip. You can play on the topology of the network by rewiring links, and so you can control, you can create and destroy patterns. This is a picture of a paper of my group that has been put on the cover on the APGB some years ago, where we show that indeed you can, at the beginning, you have this very regular pattern, but then adding short links in the middle, your pattern is localized to one side of your network. So you can play with such kind of stuff. At the end is always study the emergence of this instability. And what else? Okay, okay, this is very fast. You can study random walk where now there is some constraint on the nodes. So where now each node can only contain 1 walker, 2 walkers, 10 walkers. And this induces some modification in the problem. Is what you told you, Stefanella, last time. The virus cannot enter in a city if everybody is already infected. So in some sense, if a city has 1,000 inhabitants, so only 1,000 of virus can enter. Of course, more virus can enter, but you cannot see them because the person are already infected. So by taking into account a sort of crowding, you can restudy a random walk which has some very interesting features. And okay, here is a random walk. I think someone asked last time or time before, what happens to random walk on temporal network? This can be done. can be studied. There is this memory effect that I showed you briefly last time, but there are 2 papers, so if you're interested, you can have a look at it. And okay, as the last one, then I stop. I spoke about this at the first lecture about this non-normality. If you remember the fact that a linear matrix, if it's not symmetric, can have this jump in the solution. And then if the system is linear, it goes to 0. But if the system is not linear, this jump can go far away from the equilibrium and so create a new phenomenon. Because now you have a network, you can use the fact that the network is non-symmetric. And so this kind of non-normal network can emphasize even more this, this jump away from the equilibrium solution. And so this class of non-normal network have been recently introduced and studied by Marbo Aslani. And so it's a very active field where you can really understand what happened. So you can have a system which is stable linearly, but because the system is non-linear, because the network is non-normal, you can have pattern where you are not expected to see pattern because of the linear stability analysis. And I think, okay, yeah, you can use delays, you can use, okay, Cartesian product, and we essentially have a preprint using relativistic theory. So you have a finite speed propagation. So up to now, because I use a diffusion equation, the propagation is infinite, while in reality it's not the case. If you think of infection, it takes some time because the infection goes from A to B. And so in this paper, we studied what happened if you modify the diffusion equation by taking into account a finite propagation speed, and there are some interesting results that can be proven. Okay, so I think I stop here. It's already 20 past 8.
Wait, the paper on delay, which one? Can you?
Yes. Yeah. So here we start the fact that, of course, it takes some time for some reaction to occur. The delay can be the in node, so the reaction are delayed on the node, or the delay is because it takes some time to cross across the link. Mm-hmm. So the delay is across the link in the diffusion part. And so in this paper, we studied so the impact of the delay again for the emergence of Turing pattern. What is important is here that you can have this instability with only one species. So in the case of without delay, this is impossible. Turing proved that you need at least 2 species to have instability. But using delay, you can have instability with only one species. In some sense, it's like you have a ghost species, which is your image passed in the time. And this shows that you can prove the emergence of Turing instability also in delayed system. But the paper is in the Dropbox, so if you want...
Also, this one, the relativistic... Also
the paper that I put on everything is inside. Yeah, okay. That's why I just pass very quickly on each one, just to say, open your ears, and if you're interested, just ask Stefanella. She has all the papers, and so have a look at the papers and ask me if you're interested.
Great, no, very interesting. We have here Victor that is very much relativistic, and in fact, speaking about relativistic interaction, there is a work by people in Milano. Mm-hmm. They review classical interaction, gravitational interaction with, for example, from galaxy with the relativistic effect.
Okay, so in this paper, we wrote the title relativistic, even if the referee doesn't like, but there is no relativity, there is no Lorentz effect. Here, relativity is because there is a finite propagation speed as the light.
Yes, but, no, but it's also in that case also is the light.
Okay. So here there is no Lorentz law, there is no Einstein, and so on. There's just finite propagation. And this equation called Cattaneo equation, which is a modified equation of diffusion. So it's also called the telegraph equation.
Just for sort of sake of seeing it, like pointing that out, because I mean the paper that Stefanella thought about, like that from the people from Milano, they sort of discussed this idea of implementing time delayed interaction to sort of try to model the I believe was the galaxy dynamics, right? without the need of dark matter and dark energy.
It's very interesting because they show that there is no need of dark matter if you take in account of.
Okay, so if you, I don't know if you can send me the paper, the reference, I will be interested in reading.
Yeah, in fact, we are thinking to have a special volume about this alternative model. So maybe we can talk about you writing one of these papers because they show the group of Milan is very interesting because they show that sometimes if you look at the problem, putting the right, taking account of the right thing, you don't need an extra thing, you know. For example, they also do some molecular, some atomic dynamic or molecular dynamic without quantum mechanics, because they also take into account of some other stuff. So very interesting to see from there are no contradiction if you take into account of the, you know, the light propagates the information is a finite speed and so on, so on. So it's very, actually I send it to you,
Yeah, okay, thank you.
Thank you very much. It was wonderful, wonderful. In fact, I would like you just again that the next time you give another course just about this stuff, you know, like for example, the multi-network is very interesting for us because, for example, in epidemics, of course, in Rio we have the metros, the train, the bus, and then on top people move by car, or you know, this can be a sort of diffusion of. So yeah, you can also couple this with diffusion now that gives people go by foot.
You can also think that each layer is a different community. So you can have a community of persons that interact among them, another community that interact among them, and maybe one person is part of both communities. I mean, community because they work together, because they had sport together, because they, I don't know, live together. And so you can also stratify your society across these layers and study the interaction in between layers and across layers.
Also, this is true for epidemics as well. You know?
Yeah, of course. Yeah, I'm thinking of epidemics.
Yeah, the residents and the tourists, you know. yeah, definitely. Okay, great. So students, question? I think I will do a Google Classroom to put all these materials. I mean, it's easier so people can have access. So yes, if not, we already, I'm already asked you for another mini course about that. since I am sure we will look closely to some of we work through some of this paper and we'll ask.
I send you everything so you can share with your student or your colleagues, and who is interested, really don't hesitate to drop me a mail. I try to answer as fast as I can. We can organize a chat if you want more details, or use my iPad to write notes and do computation in real times together if you're interested.
No, it was very interesting to see the calculation. That's very good because
I think because this is still a school, I think it's a good place where to do some computation.
Exactly.
They're not so easy, but no difficult anymore, so it can be done.
No, perfect. It was great. Thank you very much. So students, you can comment. Well, let's thank Timoteo first of all. So you can open them there for this wonderful Minicourse. So like you can open the microphone and let's clap together. So
thank you to you.
Thank you. And so just to remind that all the video of Timoteo will be first in the first page of the school, but then there is a personal page of the mini course where you can find the slides that he will send me of the last lecture, this lecture, and the video. And you can find also the videos of the other mini courses. So if you miss some, we have a library there, so people can access to other mini courses. So this is the idea to form a library. And also to mention that the next speaker in October is Mark Levy from UPenn. So also Timoteo, maybe people from there will be interested. He will give a course on Hamiltonian mechanics.
Yeah. So if you send me or to the person already registered the links, we try to do our best to attend the school.
Yeah, because of course it's not easy to have also Mark Levy. Everyone is busy, and he's the head of the department there too. So I can imagine that. And so it's also great to have also Mark with us. So we should all take advantage of all these great people that take part. Okay, thank you very much, Timoteo.
Thank you, Theo.
And we'll be in touch. Bye,
yeah, of course.
bye.
Ciao, ciao. Bye.
Ciao, ciao. Ciao.